If you've ever used a set or a map from the standard library in C++, chances are that under the hood your data is being organized in a red-black tree. So what is a red-black tree, what problem is it solving, and how does it work? Well, fundamentally, a red-black tree is just a type of binary search tree. You probably know that BSTs store sorted data in a tree organized such that any node's left child will always contain a lesser value than the parent and its right child will contain a greater value. This allows values to be searched, inserted, and deleted with a worst case time of O of h, where h is the height of the tree, which is ideally time about O log n. However, basic BSTs can become unbalanced, resulting in the time complexity degrading towards O of n. This is where self-balancing trees like red-black trees come in. In the case of red-black trees, they efficiently reorganize the nodes upon insertion and deletion according to rules that guarantee a tree with a max height of 2 log n plus 1. This means the worst case time complexity for search, insertion, and deletion are in the order of log n, a clear improvement on a normal BST worst case.
Note that because red-black trees are a type of binary search tree, they have the limitation of only being able to store data that's orderable.
Before we go over the properties, note the black dots coming out of each node where there's a missing child. We call those null nodes, and they account for all the leaves of the tree. They'll become important later on.
Okay, so here are the 5 key properties.
Property 1 is each node must either be red or black. Property 2 is the root must always be black.
Property 3 is that all null nodes are black.
Property 4 is that a red node can't have red children. And property 5 is that for every node, all paths from that node to the leaf must contain an equal number of black nodes. We call that number the black height, and maintaining an equal black height from the root node to the bottom of every branch is the key that guarantees a relatively balanced tree. But in order to preserve these properties, there's a lengthy set of rules that must be followed upon insertion or deletion of nodes. But before I show you those rules, I have to introduce the left and right rotations. These are binary tree operations that move the node up a layer without violating BST properties.
For example, a left rotation is possible between a node n and its right child c. What happened is c takes the place of n in the tree, and then n becomes the left child of c. The symmetrical opposite is the case for the right rotation. For a node n with a left child c, a right rotation can occur. C takes the place of n in the tree, and then n takes the place of c's right child.
Okay, so now for the insertion and deletion rules. So when we're inserting a node, we insert the node as we would for a normal binary tree, as a red node.
In this example, since the new node's parent is black, no further action is needed because there are no violations of the properties. But if the parent is red, then a red-black tree property must have been violated, so we're going to consider 3 cases on how to resolve this. All these cases are symmetrical, so you can flip the left and right and the rules will still fix the tree.
In these examples, we'll call the newly inserted node Z.
So in case 1, we add a red node to the tree, and its parent is red and its uncle is red, then there's a violation. That means we have to turn the uncle and the parent to black, and then we put the grandparent as red. But this causes another violation, so we have to keep going up the tree with the same pattern. And then at the end, we have to ensure that the root node is black, because that's one of the properties. So we do that, and now we're done. Please note that dealing with this case might take up to time O log n, because you might have to travel all the way up the tree to fix all the conflicts. For case 2, we're looking at a situation where the node Z is a right child, and Z's right uncle is a black node. In this case it is because it's a null leaf. So we straighten it out by single rotate left between Z and its parent, and this brings us straight to case 3.
So in case 3, Z is a left child, Z's uncle is once again a right black node. To fix this situation, we just need to do a single rotate right between Z's parent and Z's grandparent. Then we just switch the colors of the 2 nodes we just rotated, and we'll fix the tree. So that's insertion in a red-black tree. The time to find the node is in the order of log n, and the time to fix a node is at worst in the order of log n. So the insertion as a whole has a time complexity of O log n. Now let's move on to deletion. To delete a node in a red-black tree, we want to start off the same way as we would in a BST. So say we want to delete 2, 3, 3, 4.
After we find the node, we want to go into its left subtree and find the greatest node in the left subtree, otherwise known as the in-order predecessor. And if that node is red, then we can just remove it and there won't be a violation. But when we want to copy a value from a node that's black, things get complicated when we remove it, because property 5 is no longer held.
So in a situation like this, when we remove node x, its child will become x's parent's child as normal.
Then we're going to temporarily change that child to something called a double black node. A double black node adds 2 to the black height, which maintains property 5 of equal black height on all the branches. However, double black nodes are a violation of property 1, which states that nodes must either be black or red. So we need to fix the tree so that it no longer needs a double black node. To do that, we have 4 more symmetrical cases to deal with. In these cases, we'll call the double black node Z, and then S will be Z's sibling and P will be its parent.
And when reading the chart, note that the process can start from any of the cases, as long as we have a double black node in the right position.
Okay, so here we have an example of case 1. Here we have Z, and its sibling S is a red right child. So what we do is we perform a left rotation from S to P, and then we swap their colors. And that's the end of case 1.
So completing case 1 can bring us to either case 2, 3 or 4, but in this case it brings us to case 2. Note that Z is always the null leaf, so the new S is this node.
And the conditions for case 2 are that S is a black rat child, and that both of S's children are black, which they are because they're null leaves. So in this situation, we want to push the blackness up like we did in insertion case 1. So this one to red and this one to black. Notice that now we can change the double black node back to a normal null leaf because the black height is equivalent for every branch. And like insertion case 1, if there are any violations, once we change the colors, we have to keep going up the tree fixing the violations. But in this case, there are no further violations, so the tree is fixed.
Because of the step of having to push the blackness up, this step can take up to time O log of n.
Okay, so here's an example of case 3. We want to delete node number 4664. And so we go down and get node number 4646, and we're left with a double black node. So how do we resolve this? Well, if S, the double black node sibling, is a black right child, which it is, and S's left child is red, which it is, and S's right child is black, which it is, then the steps are to rotate right from S to its left child, and then switch their colors. Completing case 3 will always bring us to case 4.
Case 4 is when S is a black right child, and S's right child is red. So in this case, we rotate left from S to P. Then we need to change S's color to that of P, which it already is. Then we need to change P's color to black, which it already is. And then we need to change S's right child to black. And now we can remove the double blackness on the null leaf because the black height is equal for every branch. Now we're left with a fixed tree. Just like insertion, the worst case time complexity is in the order of log n, because the time to find the node to delete is in the order of log n, and the time to actually delete the node can take up to time O log n. So that is how a red-black tree functions. Before I go, here are some limitations of red-black trees.
Compared to arrays or hash tables, they're not optimal for small datasets because they have a lot of overhead.
There can only be 2 children per node, so it's less suitable for very large datasets than other solutions like B-trees. They're bad for simultaneous access because you have to lock the tree and do all the operations every time you interact with the tree. They're bad for disk storage because there's a large amount of disk I/O. They're more designed for in-memory use. Lastly, AVL trees offer a better worst-case lookup time because they have a more strict balancing. But the stricter balancing also introduces greater overhead for insertions and deletions. Okay, thank you for watching.